Greetings. Ooh, I got a case of the Mondays. This is so weird. This is weird. So I'm trying to get mentally ready to talk to a computer screen while several cats are looking at me like I'm weird. I'm Mama Kitty. What am I doing? Ooh, Simba. All right, we live in a zoo. So today we are going to look at Newton's second law and then eventually apply that to Newton's third law. So Newton's second law, F is equal to ma. First of all, let me review what you guys need to know for your test. You need to know relationships, direct proportionalities, inverse proportionalities for F is equal to ma, variations like impulse, momentum. As this goes up, that goes down. As this goes up, that goes down. As this goes down, that goes up. Velocities, accelerate, right? Remember how I said, like, if the time goes down, like on the denominator, if the time goes down, then the other side, it goes up, because the direct proportionalities are numerator to numerator. But on the denominator, if that goes down, then this goes up. Like if I run the same distance in less time, that means my speed has to be greater. So we'll review that more just to make sure you understand. But direct and inverse proportionalities to concepts. I'm not going to ever make you solve for x, but we have to know how x affects y, how y affects z. That's applicable. You can apply that in your life, understanding how the different factors, variables affect each other. So let's get into law. Sum of the forces directly proportional to the mass times the acceleration in a specific direction. Today's application is going to be y, because I had to pick something. Get it? Stupid. Sum of all the different forces in the y direction is going to be directly proportional to the stuff of the object we're looking at times that object's acceleration, change in velocity in regard to time. You could even look at it as change in position, because everything takes time. It still comes back to everything takes time. In other words, if you change position, you have to be displacing. If you displaced, it took time to displace. If it took you time to displace, that meant you were moving. And if you have, that meant you were moving. And so if you're moving, you have speed, you have velocity, and directional movement is velocity. And if you changed velocity, you went from not moving to moving, you changed velocity, so therefore you had to have acceleration. So a lot of these things are just implied. When we say acceleration, or when we say unbalanced forces change motion, acceleration can be implied, can be inferred because of what I just babbled about. Ooh, it's one of those days. So, F is equal to ma, which is the kinetic side. Forces, which is the kinematic side. Movement. The object is a kinematic variable. Object's motion. Unbalanced forces directly proportional to the changes in an object's motion. Okay. For today, I'm going to introduce you to how we discuss forces. It's called free body diagrams. I know my art is not the best, but you get the point. So what a free body diagram is, it's a drawing, a very basic drawing, of whatever the object you want to look at Newton's second law is. And that object has to be free and clear of any other drawings of any other objects. I'll give you an example. If I drew, if I was holding this pen, why a pen? If I'm holding this ball in my hand, right? And I was interested in looking at all the different forces that the ball feels, that the baseball feels. Okay. And I said, let me draw that ball and then look at all the different. If I drew and the hand, if I drew two objects instead of one object, understanding the forces gets very confusing. I'll give you an example. G, okay, let's see, force from hand. So, let's see, these are my fingertips. So if I drew the ball and the hand, these arrows don't, it's very clear that these arrows are ball force arrows. In other words, the ball feels planet Earth pulling down, but that arrow is pointing to the hand. So is that what the hand feels from the ball? It is. So that gets very confusing. What does this arrow represent? Who is feeling this arrow? Well, this arrow represents what the ball feels from the hand, but it looks like it's something pushing up on the hand. So that's why for a free body diagram, if we're looking at forces that an object feels, we have to draw the object free and clear of any other objects to avoid confusion. So now we can say, what does the ball feel? The ball feels planet Earth pulling down, and the ball feels an upward push from my hand. Free and clear of all the other objects. You just have to define which object you're talking about. So I have an example of a vertical jump. Okay. Now, this has to be a very specific part of the vertical jump, right? So, let's say we paused it. And we said, okay, what are we feeling right now? And if we had a fancy scale that could give us real-time forces and stuff in 3 dimensions, it's called a force plate, but it's a 3-dimensional scale. It can give us forces in the Y, it can give us friction forces in the X, and it can give us friction forces in the Z. For this example, I am not looking at X's and Z's, I'm just looking at Y's, okay? Just looking at Y's, because it's the Y forces that I can balance my checkbook with gravity. Since gravity is in our Y, how we perceive Y, I'm only looking at Y compared to Y. I can only compare apples and oranges, okay? So here's the point. I can look at this as, hey, what does the ground feel from you? If you're doing the vertical jump, what does the ground feel? Well, the ground feels a downward push. That's what the ground feels, right? In other words, if you had a grape and you wanted to smush if the grape was on the ground, the grape would feel a downward push from you, and then the grape would feel an upward push from the ground, and together y'all would. So when you step on the ground feels negative push from you. Another way to look at this is if you're walking on the beach on the sand and you leave a footprint, that's because the beach felt downward push from your foot. So this is what the ground feels from you. Okay. Now, Newton's third law says that for every force any object feels, in this case, the ground feels a force. Forces have to be delivered by things, by objects. So the force is a push. It's a compression. The object that delivered this force to the ground is you. Newton's third law says that for every force that an object feels from some other object, there's an equal in magnitude and opposite reactionary force that the other object must feel back. So in other words, if you're not touching the ground doesn't touch you. If you touch the ground's going to be touching you. And those forces have to be equal and opposite. Equal in magnitude, opposite direction. If the answer is nothing, if the ground feels nothing from you, you feel nothing from the ground. If you feel a little bit from the ground feels a little bit from you. If you feel a lot from the ground feels a lot from you. Comme ça. So, the point is, Newton's third law, for every force an object feels, there's an equal in magnitude yet opposite counterforce some other object must feel. Newton's third law is a kinetic law. It's a force law. So the ground feels this from you. It is impossible for you not to feel this back from the ground. Now, Why is this extra little arrow here? Well, that's what you feel from planet Earth. Okay, now, technically the ground feels some stuff from planet Earth too, but we can look at it as this is part of planet Earth. And remember, objects can't feel themselves. If the ground feels this from you, you must feel this back from ground. Okay? Ground reaction force. In other words, if you're not pushing on the ground, it's not pushing back on you. So the only way to get that force back is for you to first push. What came first, chicken or the egg? Well, you got to push first for the ground to give you something back. And it's actually that ground reaction force that's going to influence your motion. This is very important. Because remember, last week I said you don't influence yourself. You impart energy or force onto other things. And then because of Newton's third law, those things import forces back on you. And that's what changes your motion. That's what moves you. So next time you're jogging on the road, I want you to think about it in another way. You are trying to move the road, but the road isn't going anywhere. So if you're trying to move the road this way, you get back. Now, that's friction. We'll get into friction forces on Wednesday. But the point is that if you're running this way, right? You're running this way. Think about it. If you were on gravel, or let's say you're running on the beach. I think this is a better example. If you're running on the beach, where are you kicking sand? If I'm running this way on the beach, I'm kicking sand behind me. And I'm kicking sand behind me or in the opposite direction because that's the force that the beach feels from me. The beach feels force this way. So what do I get back from the beach? I get a force this way back from the beach. And that's the force that's actually propelling me forward, or as I proceed forward. If I turn this way, how am I kicking sand? That's what the sand feels. That's what the beach feels. So if the beach feels this, what do I feel? The opposite. Okay? We do not move ourselves. Indirectly, we move ourselves, but we don't move ourselves directly. How this works is we are constantly, when we're moving around, we are constantly trying to move other things like the ground. And we get back reactionary forces from it that actually move ourselves. To give you a couple more examples of how we don't move ourselves, imagine your whole life, you're walking, you're running, you're used to the ground reaction forces and the friction reaction forces. Then all of a sudden you go skating, ice skating, roller skating. You don't move yourself as efficiently, right? You still have the same joints, you still have the same muscles, you still have the same everything. So what's changed? The reaction back to you has changed. Another way to look at this too is if you were doing a vertical jump, you got $100 for every inch you jumped up in the air, so you know your effort is going to be maximum. Who's going higher? When you jump on a solid cement surface, or if you do a vertical jump on a beach volleyball court? So think about it. Muscles the same, effort the same, joints the same, mass the same, weight the same. But yet on the cement you go higher than on the sand volleyball court. What changed? Cement down, but the cement ain't going anywhere. So you get all of that energy back, not all of it, but a big chunk of it back in reaction forces. When you jump in the sand, you actually move the sand. Some of your energy that you gave the sand literally went to the sand, pushing the sand down. So not all of that energy came back to you, accelerating the sand down. So you didn't get as much back from the ground in that case. Why is this important? It is important to see that we do not move ourselves because those are variables that some of you will need to be able to work on. Shoes. In other words, if we're getting back stuff from the environment, we need to know what's interacting with the environment. Shoe design, wear and tear on shoes, surfaces on shoes, athletic trainers, right? Don't we want to create safe surfaces? Basketball court might be humid and wet, or too much dirt that will get into the imperfect surfaces between our foot and cause us to slide around, right? So we need to monitor environment, because it's the environment that's going to be returning forces back to us via reactionary forces, and those are the things that's actually going to move us. I'll give you another example of ground reaction forces, and sometimes they can be too much. Turf. When field turf first came about, man, people would be running fast. You wanted to play on turf because you ran faster. Why? Because you got back more efficient energy back. The force you gave the turf was about what the turf gave you. Nothing, no sand going down on turf. But the problem is that those great forces you were getting back had to travel back through your body. People were blowing out knees. If you got tackled and your head hit that solid surface, that cement, concussions, they were like, bro, this is too efficient. The surface was too solid in terms of efficiency. So they actually had to do some modified turf where they put bits of rubber and imperfect surfaces to more mimic grass. Because if you think about it, when you're cutting and planting on grass, when you cut and plant, the grass and the topsoil sometimes moves with you. Here's one way to look at it. If in football, if you run a bunch of plays in one area, the grass is going to start to wear away. Wimbledon, you see the same thing. You start to see wear marks. So that was when the ground reaction forces were too high, when they had the original turf, field turf. Dude, people were getting hurt left and right. It wasn't safe. Or just imagine falling on that turf on your shoulder, blowing out an AC or a collarbone break, a clavicle break. So today's lecture is about ground reaction forces and how that is important for Newton's third law. Lucy, thank you. Newton's third law. For every force an object feels, there's an equal in magnitude yet opposite counterforce some other object must feel. Newton's third law to a biomechanist is not just action-reaction. And the reason is because action infers motion. And Newton's third law, it's forces that are trying to cause motion, but you may not have motion involved in them at all. Because Newton's third law is all about forces, not about motion. So think of holding the ball in my hand. There's no motion and action. But yet I have Newton's third law being applied to the ball, planet Earth pulling down, my hand pushing up. I have Newton's third law applied to my hand, ball pushing down, planet Earth pulling down. How would I state Newton's third law with these forces? Well, what does the ball feel? One non-contact and one contact. I'll do them one at a time. The ball feels a positive Y push from my hand. How much? Who cares? Well, I know it's the weight of the ball, but neither here nor there. What's important for this class is what it is and where it is. What it is meaning the force from the object, not like the magnitude. I'll give you magnitudes. You need equipment to figure out magnitudes. So any magnitudes in terms of amounts I'll give to you. But more important than that is what you can figure out. You can figure out what the force is in terms of the type and from what object, and you can see direction. That's what's important. So what does the ball feel? What does the ball feel? Ball feels a positive push from my hand. That's a compression. Ball feels this from my hand. So Newton's third law says, well, if the ball feels this from my hand must feel this back from the ball. If the ball feels this from my hand, a positive Y force from my hand must feel a negative Y force from the ball. That's it. For every force an object feels, there's an equal in magnitude yet opposite directional counterforce some object must feel. Newton's third law applies to non-contact forces as well. What does the ball feel from gravity from planet Earth? Well, we could take my hand out of it and say the ball feels a negative y pull from the center of the planet Earth. Now remember, that pull isn't from the ground. It's passing through the ground, but it's not from the ground. What I mean by that is if I dug a hole a mile deep and dropped the ball, it would go way past the ground. It'd go as far down until something stops it. This is the center of the planet. And so Newton's third law says, well, if the ball feels a 8-ounce pull, a half-pound pull from the center of the planet Earth, it's impossible for there not to be a half-pound pull pulling up at the center of planet Earth from the ball. And that's true. That's so cool. 3,000 miles down, there is a little arrow of the ball pulling up on planet Earth. Now, does planet Earth really notice it? But it's there. It's there. Let's do a bigger example of Newton's third law with gravity. The Earth pulls on the moon. That's how we get tides, right? It's from the moon's pullback. If we didn't have the moon there, we wouldn't have tides. They pull on each other, in other words. And the magnitude of that pull is how much stuff those objects have and how close or far apart they are away. But the point is that Newton's third law applies to gravity as well. Planet Earth is pulling on this pin, pin is pulling on planet Earth. The pin has gravity to me. I have gravity on the pin. It's ridiculously small and immeasurable. But the reason we can't really see it is because we're on Earth. If you took 2 quarters, and you put them in orbit, constant free fall around Earth, and you put them an inch apart, in a few hours, they're going to be touching because they're pulling on each other. They have gravity towards each other. It's impossible for one quarter to be pulling on the other without the other quarter pulling back. Okay? So Newton's third law, for every force an object feels, there must be an equal in magnitude and opposite direction counterforce some other object must feel. So let's get back to how we got to Newton's third law. We started with Newton's first law, inertia. Objects resist change in their motion because they're made of stuff. And the more stuff they have, the more they're going to resist change to their motion. Newton also noticed with his first law is objects cannot move themselves. This baseball cannot move itself. It cannot import an unbalanced force on itself. I can import a force on myself, but that force must be balanced. In other words, my cheek feels this, Newton's third law, my hand feels that. This is what my cheek feels, this is what my hand feels. And they have to feel the same thing, equal and opposite. So the only way to have an unbalanced force on an object is to have some other object supply that unbalanced force. So, first law, inertia, object's mass. That is a kinematic, a motion law. Newton slipped his first law into his second law. That's mass of the ball. Only forces outside, external forces, can influence that ball's motion. Things outside, the other side of the fence of the ball. Come in. My dad. So only things outside of the ball's influence, right? So if this is the ball, outside of the ball's influence, so things like the bat, what does the ball feel from the bat? What does the ball feel from the glove? What does the ball feel from rolling on the ground? Okay? So Newton's law says, hey, the only thing that could change the motion of this ball are other things influencing the ball. The pitcher's hands, wind, air, other things. And then finally, Newton realized this. Well, if other things are trying to influence this ball's motion, that must mean this ball in return is trying to influence those other things' motion. In other words, it's impossible for the ball to feel the pitcher's fingers and the pitcher's fingers not feel the ball back. It's impossible for the ball to feel the wind from the air, but the air not feel the ball back. It's impossible for the ball to feel the bat and the bat not feel the ball. That's Newton's third law. Okay, so how does it apply to us is that we have to realize and understand that our effort can't move ourselves. It's the reaction that we can actually get from some other object. We have to have some other object there to give us our effort back to us. If you tried to do a vertical jump on roller skates, right? It's not our effort. It's what is our effort being applied to, and then what does that object give us back in return? That's what's actually moving us. When we jump up in the air, it is not us that's getting us up off the air. It's whatever we're pushing down on. Whatever we're pushing down on gives us force back in the opposite direction. That's what's actually making us jump in the air. For us to be able to jump in the air, we are actually trying to push something down in order for that thing to therefore push us up. Okay? That is our lecture today. I'm going to do office hours. I'm going to try to do this, not virtual office hours, YouTube live office hours. I'm going to send out a class email, and on Wednesday, I'm going to give 30 minutes. Hey, maybe it goes for an hour. I don't care. During the day, maybe during our standard standard class time, like 8:30 to 9:20, where I'll be on YouTube live, and you guys can, hey, Dr. Campbell, what about this? What about this? Can you go over this? Can you go over this? And then I can just clarify some stuff, okay? All right, let's go with watched, but the number one after watched. So not an exclamation point, just the number one. Watched with the number one. Why not? All right, guys. Y'all have a good one.